Welcome to another awkward question from the question bank. This one's reference is 820439 and it's a question about tail rotors and relates to helicopter POF. Let's have a look at the question. The main rotor is rotating anti-clockwise when viewed from above. If right pedal is applied, and the answer options are: the nose will move right, aircraft will climb. The nose will move right and the aircraft will descend. The nose will move left and the aircraft will climb. And the nose will move left and the aircraft will descend. Straight away, as pilots, we can rule two of those out. In the question, with it stating the main rotor rotating anti-clockwise, well, that puts us in mind of something like an R22, R44. So the rotors are rotating in the same direction as those aircraft. It would be the opposite for something like a Cadbury or a Squirrel or something like that. We can rule two of those out straight away. With right pedal, the nose will not move left. So straight away we can rule out C and D. It leaves us with a 50-50. It's got to be A and B. Will it climb though, or will it descend? I guess that's the question, right? How do we know? Well, here's a transmission system from an aircraft. Two engines supplying power via the output shafts into the input shafts, and then the gearing into the main rotor gearbox. From the main rotor gearbox, there is another feed from the accessories that goes down to the tail to drive via the intermediate gearbox and the tail rotor gearbox, the tail rotor. What we can say from this is that that whole system is mechanically linked. So what happens when we apply pitch? Well, on the main rotor head, when we apply pitch, particularly collective pitch, we put pitch on all of the blades of the rotor. With the collective, there are anticipators associated with them that anticipate that collective input and allow the governor to put fuel in ahead of the drag building up. But I think we can agree that when we apply pitch, we increase the drag on the rotor head. That increase in drag needs more power to overcome that drag. And usually when we apply that power, we don't see a reduction in NR. Because the anticipators sense the movement, the fuel gets put in time for that pitch to be applied. Thank you to the governor. Down at the tail rotor, the same thing happens. When we apply pitch to the tail rotor, so in our R22, we put left pedal in and we increase the pitch to bring the nose left, the same thing's happening. We've increased pitch, so we must have increased drag. If we've increased drag, the blades are going to want to slow down. So how do we compensate for that at the tail? Because there isn't an anticipator. There's not an NR sensor that's monitoring the NR of the tail rotor. It's only on the main head. So what happens? Well, the only place that the power can come from to offset that increased pitch is via that mechanical linkage from the main gearbox and the main transmission. The result of that is that we now have, from the rotor head, main rotor head, a pitch setting that now hasn't got enough power to overcome the drag for the pitch setting that it's got. And so the aircraft will, or the blades will start to slow down. Blades slowing down is a reduction in V square in the lift formula. And if that happens, we lose lift and the aircraft descends. So we can say with left pedal, when we increase the pitch on the tail rotor, therefore increase the drag, we take power away from the main transmission and the main rotor head slows down a bit. It's not much, but it's a bit, but it's enough to get less VR, velocity of rotation. And therefore we get less V square, aircraft descends when we turn in left. The opposite is true when we turn in right. When we turn in right, we don't apply right pitch on the pedal, we reduce some of the pitch on the pedal and allow the torque reaction to take over. That reduction in pitch frees up some power back to the main rotor gearbox. Now we've got an excess of power for the pitch setting we've got. Power is stronger than drag, so the blades will speed up. That results in an increase in the velocity of rotation, therefore an increase in V square. Back to the lift formula, V square increase, lift goes up, we go up. So as an experiment, we got an aircraft and videoed the response. So what I've done is we've got a primary flight display, declutter selected just to clean it up a bit, make it a bit easier to spot. The dot I'll put on the VSI and the rad out. I'll start on the rad out so you can see that, and I'll move it up to the VSI. We're going to yaw right and see what happens. The VSI at the bottom of the page, on the bottom of the primary flight display, will show us that we're yawing to the right. So there's the rad out, 8 feet set. All we're going to do is start yawing right, and straight away you can see the VSI has increased. Not much, but a bit. No increase in power, collective stayed where it is. And the rad out's gone all the way up to 17, 18 feet, just through pedal input. We'll now stop the turn, which is why the VSI has come back down, because we've applied left pedal to stop the turn. So what? Well, I think we can safely answer the question now. The main rotor is rotating anti-clockwise. If right pedal is applied, then the aircraft will move right, or the nose will move right, I should say, and the aircraft will climb. I hope that's been useful. If you come across any other awkward questions, just write in and we'll see if we can get to the bottom of them.